So the other thing that we have to use one-sided limits for is when the graphs are not defined from one side. So if we take a look at the square root of x plus 3, the square root of x plus 3 is this graph here. So the center is at -3. And we cannot approach the -3 value from this side because there's no graph on this side. So if we were to say that this is a two-sided limit coming from this side and this side, okay, we'd have to say that the limit doesn't exist because there's no limit from one side. Okay, there's no limit from the negative side. So for these functions, we can only define the limit from one side. So as we approach the -3 value from the positive side, okay, so we can approach it from this direction. Now we can establish the limit. Okay, as it approaches that value from this side, x equals -3, yeah, the y value is tending towards 0. That's a perfectly valid limit, but we cannot define that point from both sides because it does not exist from the left-hand side. So we have to say that the limit does not exist. The same thing is for log as we approach 0. Okay, so as we approach 0, it's going to dive down to infinity, negative infinity. However, we cannot approach 0 from this side because the log function is not defined for negative numbers. So the log function as a two-sided limit doesn't exist. Okay, so I'm just going to, this is 0 from both sides. So this side going to 0 from this side, and this side, it doesn't exist. Okay, but as we approach it from the right-hand side and make it a one-sided limit, yeah, this is a one-sided limit exists. Okay, so if I approach it only from this side, yeah, we get a limit of negative infinity. It's going down to negative infinity. So it's very important to understand some functions are not defined on both sides of some values. Okay, we have to use one-sided limits in those cases. So these ones here is just some practice, so we can just work some of these out ourselves. So there are some different strategies we can use. The main thing is we want to just plug in and make sure that the limit there's actually a problem with this limit. So when I plug in, I get 0 times 8 over 0, which is 0 over 0. Yeah, that's a problem. Okay, so I'm going to have to do something to evaluate this limit. So what I can do in this case is, well, this 0 is a problem, and I can cancel out with that 0 in the numerator. And so I end up with this limit as x goes to 3, and we're just left with x plus 5. So we can algebraically rearrange these expressions and then just plug in. So we get a limit at 8. In fact, this is a linear function with a hole at x equals 3, y equals 8. This one here, we should try to imagine what's going on here. We're going to end up with 1 over 0. But because this 0, we have to make sure we know which side of 0 we're approaching from. So if we're approaching from plus 3 from the positive side, it's going to be positive 0, so we should end up with positive infinity here. Okay, so if we're to sketch the graph of this, the graph should look like this. We have a vertical asymptote at 3, and from this side it's going to be positive, and this side is heading towards a negative. Okay, and then we have our asymptotes going out like this. Okay, graphing this, I can sketch that as well. There's a hole there. This one here, can we algebraically simplify that? Well, first of all, let's make sure that this is a problem. We do get 0 over 0. So again, this is a problem. So is there something we can do to algebraically simplify this? Well, this is a bit of a trick, but we know that the square root of x minus 3 times the square root of x minus 3 is x minus 3. So I'm going to express the numerator like this. And then I'm able to algebraically get rid of that divide by 0. Well, if I can get rid of the divide by 0, I can evaluate that limit as 0. Okay. This one here, as we approach from the positive side, ooh, this one I forgot. We cannot approach the 3 in the denominator from both sides. So although we can algebraically simplify this, we have to say that this does not exist. Okay, this is a big problem because we have to remember, I forgot, that this is a one-sided limit. We can only approach 3 from the positive side. So this one here, well, we can do the exact same thing, but now we can actually work out the limit because now we're approaching it from one side versus the other. So we can cancel these out, and this is equal to square root of 0, which is 0. Okay, and again, I was able to do this because I'm only approaching from the positive side. Okay. And lastly, we can look at the endpoint behavior. Okay, this endpoint behavior of this is when we can use our strong over weak argument. We can't use strong over weak arguments here, okay, because these are not endpoint behavior. These are local behavior. So we want to distinguish when we're dealing with one versus the other. This being endpoint behavior, we can just look at the relative strengths of functions. Well, this is equivalent strengths. So what we can do is make the argument that this plus 5 and minus 3 at large values of x are insignificant. And we can simplify that ratio to 1 over 2. Here we have, in the numerator, a degree 2. In the denominator, we have a degree 5. Well, the denominator is going to go to negative infinity very, very quickly. Okay, and it's going to be more powerful. So we have a strong over, or sorry, weak over strong situation. So that's going to tend to 0. Here we have a weak over even weaker. There's 100 here, so it makes this big, but remember that the power of infinity, even though it's a weak function, it will eventually get to infinity, and that 100 does not compare to any large number near infinity. So we end up with, in this case, a strong, which is actually not that strong, but basically a weak over even weaker. So it's a weak, strong over weak situation, so this will tend to infinity. And this one here, although the denominator is a very big power of polynomial, it still does not compare. Although it's strong on bottom, it's stronger on top. So we have this strong over weak situation. And that will tend to infinity. Okay, so this is a good idea to graph these to just confirm what you're seeing. These, especially these ones here, this is local behavior. These ones are a little bit hard, and we really want to make sure that this one here, we understand why that one doesn't exist as a two-sided limit, but exists as a one-sided limit. Okay, so we should really check that graph out.